Thank you, Katsuya, for this presentation. So I am very happy to be here and to present this seminar. So I am Dominique Luneau, professor in University Claude Bernard. Katsuya gave some piece of information about my curriculum and only 14. So I am French. Lyon is here. I was born in Saumur, which is a small place here, not far from the sea, along the river Loire. I first studied in Le Mans. So Le Mans, you know, was a racing car. Then I studied engineering chemistry in Clermont-Ferrand. I have my PhD in Toulouse with Professor Jean-Pierre Tuchag concerning the manganese for the system 2. At that time, already it was very fashion to research about new energy, and the photosystem was very popular. During this PhD, finally, I was more interested by magnesis. And since why I have my postdoc in IMS Okazaki for 2 years. I was working in the group of Professor Shigeo Kida, also with Okawa Sensei. Then I got my first permanent position in Grenoble as CNRS researcher. I stayed there for 12 years under the direction of Professor Paul Ray. In 2001, I was visiting professor in the University of Montreal for 1 year. Then I got my position as professor in where I stayed there since 2000. So after my postdoc in Kazaki, I get my position in CNRS, and there I start my research on molecular magnet using nitronyl nitroxide radicals. And finally, I discovered that most of the system I have studied were usable as memory system. The first, I remember the first time I start my position in Grenoble, it was in January 89. I was there for less than 1 month, and the first compound I isolated has some spin condition properties. And I will show you what is memory. So memory is general terms. Many systems will have memory. You have magnetic system, mechanical system, electrical system. What you need that the system can have 2 states for the same condition, but for going from one state to another, we don't follow the same way. So, for example, one state will be available when cooling the system, and another system will be available when heating the system. And this makes memories. So you will see that during my seminar, I will show you different systems that show memories. So I will show you some molecule-based magnets, some molecular spin transition, and valence tautomerism system. So I am a coordination chemist. So I do chemistry. So I play with atoms. And in coordination chemistry, we play with metal ions and ligands. This is the toolbox. We have the metal ions, we have the ligands, and we try to assemble the metal ion using ligands. So using metal ions and ligands, there is 2 types of molecular magnets. Molecular magnets in general terms. So the first system that people were interested in finally were extended networks. And the idea was to finally make classical magnet by a supramolecular approach. So in this way, you connect the metal ion with the ligands in extended network, and at the end, you expect to have compounds that behave like magnets. And this was very popular until the 1990s years. Then a new system arrived, which were very interesting on the point of view of molecular. In this system, we don't have an extended network. We have like a cluster in which we have a few metal ions surrounded by ligands, connected by ligands, and they behave as magnets, but they are molecules. We call them single molecule magnets. Today, in my presentation, I will focus mainly on molecular based magnets. And I will show you how we can do it using coordination chemistry and ferrimagnet. So the first work on this system were mainly done or pushed by the group of Iwamura. The idea was to connect metal ions by bridging ligands to have interaction between the metal ions and to have finally a magnetic movement which is not cancelled. So in such a way you can have magnetization. Of course, you have always to remember that to have magnetic system, we need free electrons. We need unpaired electrons. So in this approach, we have to use metal ions with unpaired electrons. Because the bridging ligands are diamagnetic, we have to use different metal ions here. So because generally in the nature, the system are always, most of the time, are anti-ferromagnetic. If the two metal ions have the same magnetic moment, of course, you will not get magnetization because the moment will cancel. So you need to use different metal ions with a big magnetic moment and a small magnetic moment. In such a way, you will have a resultant magnetic moment. So from the chemical point of view, it's more challenging because you have to find bridging ligands which are able to recognize different metal ions. You don't want to have metal 1, metal 1, metal 1. You want to have metal 1, metal 2, metal 1, metal 2, metal 1. So it's not that challenging. It's why in the turn of the at the end of the 80s, also by Inoue and the group of Gatteschi, the idea has been to use radicals as bridging ligands. So now we have radicals here, the ligands, and because they are radicals, they are unpaired electrons. So unpaired electrons means we can have magnetic properties. And now, because we have now a bridging ligand which is also magnetic, we don't need to have two different metal ions. We need to have only one type of metal ion. From the chemical point of view, it's more, I will say it's more easy because you don't need to have a radical recognizing two types of metal ions. You just need a free radical metal ions, and normally you should get some extended magnets. So there is many different possibilities. One was developed by Inoue sensei and Iwamura sensei. The idea was here to make to functionalize these several nitroxyl radicals. So you have 1, 2, 3, and using this, you can connect here manganese 2. So you have here spin 3 half. Manganese 2, you have 5 unpaired electrons. So you have a spin 5 halves, and using this, Inoue was able to make a compound that behave like a magnet with a Curie temperature of 50 Kelvin, which is quite high. In Grenoble, with Paul, we use another approach. The approach was to use nitronyl-nitroxide radicals. So nitronyl-nitroxide radicals, it's here, the previous transparent here is nitroxide. Nitroxide is the NO group with the non-paired electron. Nitronyl-nitroxide, you have 2 NO groups and 1 unpaired electron, but the unpaired electron, in fact, is completely delocalized on the 2 NO groups. So this is very interesting because many studies have been made, especially by polarized fraction. So I am a professor of chemistry, but I teach a lot of crystallography, and I love to use crystallographic tool, and especially the X-ray of tool, but also neutron diffraction. And neutron diffraction is very interesting because neutron has a spin. So neutron can look to the magnetic structure of one atom. And if you use the polarized neutron diffraction, you can get you can map the spin density in one atom. Using polarized neutron, you can see the spin density in radicals here, but in many compounds. And here you can see that the spin density is almost the same on both ends. So it is very interesting because now we have bridging ligands. So you can connect metal ions. So I use also here manganese 2, because manganese 2 has the most free electrons, 5 electrons. So 5 electrons means large spin, 5 halves. Radical has only 1 electron, so spin 1 half. So you have a big spin, big moment, a small moment, even if they are anti-ferromagnetic, decoupled, you will have a resultant magnetic moment. But finally, it's not, when I say this, they are very interesting, bridging, but it's not so perfect. In fact, from the chemical point of view, the NO group is a weak Lewis space. So it is very difficult to coordinate to metal ions. Generally, we have to use here, we use this kind of complex because the manganese 2, when it is surrounded by hexafluoroacetyl cetonate, it becomes very acidic. And in that case, it's more easy to connect with the NO group, which is weak Lewis space. But if you do this, finally, the only thing you can do are chain compounds. But chain compounds is not enough if you want to have a magnet. If you want to have a magnet, you have to connect the metal ions in the 3 directions. So how we can increase the connectivity? If we want to increase the connectivity, we have to make the side more able to coordinate. So how we can make the ligand more able to coordinate? One way is to, when you have studied this for the the student, you are here, when you are in a coordination classroom, they will say, they will speak to you about Kellet effect. The Kellet effect is very interesting if you want to force the coordination. And it is what I have developed when I joined the group of polymers. My idea was to make the nitronyl as a Kellet ligand. If you make the Kellet means the ligand will behave like a pins, so we can tied to the metal valence. So here you have a Kellet. And when you do this, it's become more easy to coordinate metal valence. For example, here I coordinate copper, and you see I do not more need to use the hexafluoroacetyl I used before. The Kellet effect is enough to coordinate the copper. And it was the first compound I made when I arrived in Grenoble. So I arrived in Grenoble the 10th of January. At the end of January, I measure the compound on the squid magnetometer, the one you have, and at the beginning, I thought it was a problem with oxygen, but finally, because at the beginning, also for the students, you have, when you measure the magnetic properties, you have always to take care when you cool or when you eat. Sometimes it's not the same thing. And here I was, I measure this compound, so I measure from room temperature to room temperature, and discover this effect. So it's completely reproducible. And so when you cool, you this here, it is the product, I should explain before. This is the product of magnetic susceptibility with temperature. Here is the temperature. When the product of the magnetic susceptibility with temperature increases when you cool, this means you have ferromagnetic interaction which are dominant. So here you have a system in which copper and the rental. So the copper is 1 spin-half, the nitroxide 1 spin-half, 2. So for 1 spin-half, the value of the chi is 0.4. So here you see that we have 1.2 because we have 1, 2, 3. 3 times 1.4 is 1.4. Here this means that we have almost a value for uncoupled magnetic system. Then chi-T increase because you have small ferromagnetic interaction. Then at low temperature, you have a strong decrease of the chi-T value. And when you eat, you have not a superposition, but you have an external loop, and you have to go almost to 60 Kelvin to reach the first. So this is this means you have bistability. This means you have memory system. So when you are here at 50 Kelvin, you can be in this state, or you can be in this. And cooling or heating are not the same. So the reason why we have ferromagnetic interaction here, but when we are here, we have what's happened. In fact, we have studied the crystal structure at room temperature. This is the room temperature. The plane of the radical here and the plane of the EX2 Y2 orbital of the copper are coplanar, completely coplanar. So in that case, you favor ferromagnetic interaction. But when you go at low temperature, there is a small distortion of the figures regarding the copper. So you have no more copper molecule, and the interaction becomes anti-ferromagnetic. So if you, in the textbook, when you learn about spin transition, you always learn that spin transition is about the ion generally. But here it's not spin transition Q to ion, it's a spin transition Q of transition between two spin states. And the transition between two states is used at room temperature, you have ferromagnetic interaction, and at low temperature, you have anti-ferromagnetic interaction. So you switch between two instead of the molecule. And the property are the same as the classical spin transition. So at room temperature, because in with the nitroxide and metal ions, the position of the conformation of the radicals regarding the metal ions is very important for the kind of interaction, because it will the conformation will depend on if the orbital of the radical and the metal combine. So with this strategy, we use relative mediums. We have the possibility to use almost all 3D metal ions. For the 3D metal ions, we always, except for the property, we always put 3 radicals, and for the non-panaid ion, we can put 4 radicals. It is one of these components we are trying to solve this next time. So now I will show you the manganese 2. This the manganese 2, 5 radical electron and radicals, 3 radical wrong. So when we look the Caneschi product versus temperature, so at room temperature, the value is more than 2. So manganese 2, 5 electrons. The Caneschi product is 4.8. You have also 1, 2, 3. You have 1.2 for the radicals. So you expect if the radicals and the manganese 2 were not coupled, you expect something, the value of Caneschi more than 5. Here, the value is this thing that you have anti-ferromagnetic interaction. Then when you cool, Caneschi decrease. So we have confirmation that we have anti-ferromagnetic interaction, and you have here to a plateau. Why we have this plateau? Because when the 5 manganese 2 plus the 4 3 spin half of the radicals are coupled, so 3 spin halves of the 3 spin half minus 5 2 5 half for the manganese. So the resultant is the spin 1. Spin 1, Caneschi product is 1. So here, this plateau is due to the fact that the 3 radicals are anti-ferromagnetically coupled with the manganese. Then at low temperature, you have a small decrease because in the compound, in the solid, you have always 5 d orbitals. Electrons are in the 5 d orbitals. You have 3 radicals, and you will have always some recovering between the orbitals of the radicals and the orbital of the manganese. The difference between the size of the interaction will depend on this angle. For the radicals, the free electron is the p star orbital, because p star orbital is perpendicular to this plane. So the orientation of this plane regarding the orbital of the manganese 2 will makes the interaction more or less strong. So if this angle is large, the interaction will be strong, and if it is small, the interaction will be small. That is why when we try to simulate the magnetic, we need 3 interactions. So you see the sides are different because the angle between the radicals and the manganese are different. So now we have to remember that here we have nitronyl, which is skeleton. Here we have a protein. So if you want to make the current position skeleton, we have to deprotonate. But it's very interesting. If we don't deprotonate, we have isolated complex. If we deprotonate, we should be able to have the next standard network. So the idea was to use this radical almost like the oxalate, like the special oxalate, the magnetic oxalate. So in such a way to have an extended network of metal, radical, metal. And it worked quite very well. So if we use these radicals, if we use manganese 2 acetate, so we use manganese 2 acetate both as manganese 2 provider, but also because the acetate is a base, we can deprotonate the elements. And in that case, we get extended network. So you have manganese, radical, manganese, radical. This is the 2-dimensional networks. And if we look to the conformation of the ligands, when you have 3 radicals, 3 ligands like this around the metal center, you have 2 types of topology. One is delta topology and another is lambda. In 2 big systems like this, you have always the 2 topology. One is delta, lambda, delta, lambda. You have alternance of conformation around the metal axis. In fact, they are not they are not 2D because you have solar. If you have solid, this means you have a 3-dimensional organization. So in the solid state, you have the layer which are here. And because you have manganese 2, so if you look to the, it is very important because maybe you see you have, if you make any compound like this, with gelatin ligands and metal ligands, the composition is always 2 metals for 3 ligands. So here we have 2 manganese 2, so plus 4 and 3 radicals, -3. So you need 9 ions. And so for the stability, you need anions, and here the anions come in between the layers. So you have layers. The layers are made of manganese 2 and radicals, and in between the layers you have anions. And you will see that depending on the anions, we will have, depending on the anions, depending also of the subsequent, we can add different properties. So if we make the nitronyl oxide with benzene gather here, we can, in fact, it's not possible to grow crystal big enough for each single for X-ray diffraction on single crystal. We need a powder diffraction, and we have our orthochromic system. One thing very interesting is that most of the compound with this ligand always crystallize in almost approximately. Here you have one. If we look to the magnetic behavior, so here the characteristic product, we use the characteristic product, here the inverse of the magnetic susceptibility. If we look to the inverse magnetic susceptibility, you see that we have two free rise behavior, one at high temperature and another at low temperature. The one at high temperature is because you have seen before that manganese 2 and radicals are anti-ferromagnetically coupled. So here what you see is the anti-ferromagnetic interaction between the manganese 2 and radicals. But once the manganese 2 and radicals are anti-ferromagnetically coupled, you can see them like fifth either spin. So I do remember that you have two manganese 2 spin radicals. So when they are anti-ferromagnetically coupled, the resultant spin is 7/2. So it's like you have 7/2 spin which are ferromagnetically coupled. So it is why now you see this all second device. So the first device we use for the temperature in negative temperature, so on part and the second was the temperature axis in positive temperature, so ferromagnetically. So you see the ferrimagnet, so you have alternance of manganese 2 and radical discharge anti-ferromagnetically. And this behaves like a magnet. If you have at low temperature, we can see this there is this loop. And if we study the magnetization versus temperature, so the zero full magnetization, we can reach to the Curie temperature, which is about 50 Kelvin. And you have the same value if you draw the magnetization versus magnetic. So we have done this, and the question is why we have a anyway we have a ferromagnetic order, and if you look to the ferromagnetic order, finally you can see that we don't reach saturation. Normally, with two manganese 2 and 3 radicals, I told you that when they are completely anti-ferromagnetically coupled, we expect a spin of 7/2. Spin of 7/2, you expect the value of 7 for magnetic back. You see that the hysteresis loop finally saturated at 4. So it is what we call weak ferromagnetism. And this weak ferromagnetism is certainly due to counting between the spin of the layer. So the spin of the layer are not completely orthogonal to the layer, but they are counted. And because you are counted, you have a resulting magnetization, but small magnetization, which is why we have a small hysteresis. So it was one of the publications here. I show the publication not only to say it's but to see how long time it takes. And I will explain you why it takes so much time to progress with this. So it was this publication was in 2009. Then we continue to work on this system, and instead of benzimidazole, here we use imidazole. When we use imidazole, here the magnet. So the KT product is the benzimidazole, the one I showed you before, and now with imidazole. They are very, very different. And at the beginning, we were very desperate to see such a behavior because we expect to have a very magnetic behavior, and we have not. But when we look at the more in detail in the film, we see that we have here some hysteresis loop not in the magnetization, but in the magnetic susceptibility. And when we saw 6, we were thinking that maybe we have valence tautomerism. So what is valence tautomerism? Valence tautomerism is the redox enantiomers. This is compounds that are isomers that could exist with different redox steps. And it takes for us a long time to characterize this compound. First, because it takes a long time to have more crystal big enough for X-ray diffraction. Then it was not easy to prove that we have valence tautomerism. And finally, we proved that we have valence tautomerism. So what's happened is that when you do, normally the tightness should increase like this, but you have this. So at this point, finally, you have big degree. And then when you read, we have not superposition, but we we have another point to consider. We have two Curie-Weiss behavior, but the slope is the other side. So it was indicative that we have valence tautomerism, and in fact we have to understand if we have valence tautomerism, this means that some of the components change of valence state. And we have done the X-ray diffraction on Sessoli crystal more carefully, and we get the structure at 4 temperature, above the transition, close to the transition, and below the transition. And we look to the manganese ligands interatomic distance. Here we are in. You see the value, this value, which you, I know very well manganese because I have my PhD on manganese, and this is very characteristic of manganese. Manganese 2, the bonds are quite very similar, around more than 2. So there is no doubt that here we have manganese. And then if we look here, we see that we have long, but short. Long, short. And here also, when you see this is characteristic of manganese 3. Manganese 3 is not isotrope in the bond length. You have always long bond length and short bond length. So this means that we have a system of manganese 2 that become manganese 3. So we have manganese 2 with radicals and manganese 3. If you have manganese 3, this means the manganese 2 oxide. If manganese 2 oxide manganese 3, something should reduce. This means that the radicals reduce. So you have a system in which, when you decrease the temperature, you have the electron moving. The electron moves from the manganese 2 to the radical when you cool, and move again from the radical to the metal ion when you heat the system. And in fact, we should not, the formula is not the formula I showed you before, almost. We should write the formula like this. So you have manganese 2, manganese 3, and depending on the temperature, here, right, depends on the temperature. Depending on the temperature, you will have manganese 3 or manganese 3. And this is the thick. So here you have manganese 2. When you have here the manganese 2, some electrons of the manganese go to the radical. Manganese 3 oxidized and radical, some radical are reduced, but you have to keep in memory that you have 2 manganese for 3 radicals. So if you have 2 manganese, you have 2 electrons that goes on the manganese, on the radical, but on the radical you have 3. So only 2/3 of the radical will be reduced. So after this, we try to understand what makes the two components so different. So basiladol is really manganese 2 at first, it's a valence tautomerism, and the imidazole, we have valence tautomerism. So we were wondering if it was due to the anion, if it was due to the radical, or if something else can change the behavior. And effect of anion. So we have studied the effect of anion. It was the PhD of Constance Lecourt. Constance Lecourt had the summer GSPS internship here some years ago. And during his PhD, she synthesized, not only this, but she synthesized the BF4 and the PF6 compounds. The compound I showed you before was this tetride. So if you look to the crystal structure, where possible, thanks to Utah Iwamura, member of the group of Inoue Sensei. And it's very interesting because you are here, you listen to me to the seminar, but some years ago, Utah was like you, he listened to my seminar, and after the seminar, he come to me and he say, I would like to try to crystallize your compound. And we discuss, and 3 months later, he went to me and he said, oh, I succeed to crystallize your compound. So, such a very, very important. And so we can, because in this field, it's impossible to know the crystal structure, the structure of organization, to have no crystal structure. And to have today, when you want the crystal structure, you need X-ray diffraction on single crystal. Like for X-ray diffraction on single crystal, you need that the crystal are big enough. Big enough means that at least there must be 50 microns. If they are less than 50 microns, you cannot do X-ray diffraction, you cannot know the crystal structure, and of course, you cannot know what is your compound. So the major problem in this field is to get the crystal structure, because to get the crystal structure, you need to have single crystal. If you have no single crystal, you cannot prove the crystal structure. Oh. So in that case, we were able to, Utah was able to go single crystal, and we were able to solve the crystal structure with BF4 and BF6. So you can see that the crystal parameter are very close. Again, we have P21 in Sessoli. And in that case, the behavior are still we have valence tautomerism, but we have different behavior. So here, the behavior of the perchlorate I showed you before, and now with BF4 and PF6. If you look, for both we have phenolics, if you look, we have the same on the but in 2 steps. The first step, the second step. This means that you remember that this valence tautomerism is due to the fact that electrons move from the manganese to radical when you do. This means that here they move in 2 steps. The first half of the manganese gives their electron, and secondly, the second half of manganese gives their electron. So also the generally we associate the size of the hysteresis in the cooperativity, because maybe I don't say this before, but when you have some valence tautomerism compound or spin transition compound, we always say that we need cooperative. What means cooperativity? It's cooperativity is that when one molecule changes, all the other molecules will change. It's like if you are in a crowd. If you are in a crowd, if you are very tight, you cannot move, nothing happens. And if you have some freedom, you change, and all the other people change of orientation. It's the same for in spin transition or tautomerism. You need some cooperative. Here, this means that for BF4, you have middle cooperative is only for that right and the and if you look to the idea also, here we have manganese 2 and 3 radicals. At high temperature, we have manganese 2 and 3 radicals. But here we have manganese 3 and only 1/3 of radical is still alive. Well, so the question is, this 1/3 of radicals alive, is it localized or delocalized? And the first is for PF6, for example, we see that at low temperature we have this maximum. This is an indication that it may be localized in the case of PF6, and it was easy to finally if we have here at room temperature, we have this system. So one this radical are here. Now we have manganese 3, and one localized radicals. So we have a system of 2 spin 2 and 1 radicals, and we can fit the system next. So in the case of PF6, we can say that the still alive radicals are localized. In the case of the perchlorate and BF4, it's different. When you see here, of course, before calculating, because it should have a ferrimagnet, but after the transition, it's still increase. So the increase in KT is an indication that maybe we have still some ordering. And this, the fact that KT increase again is mainly an indication that for PF4 and PF6, the still alive radicals are delocalized. So in the case of the PF4, we have no more localized solution, but probably delocalized. That means that in the case of the PF4 and perchlorate, we think that the radical is completely delocalized. So it will be interesting to measure the electrical conductivity at low temperature to see if the electrons are completely delocalized. Then this was done in Hiroshima by Constance, Yuta, and Selena. So she studied the effect of pressure on this condition. So when you study the effect of pressure, you see that when you increase the pressure, the transition is moved at higher temperature, which is normal because you increase the pressure. So we have we have radically concise time depending on the substituent here. If the substituent are hydrogen, so in the we have this. This is the I showed you before. But when we collaborate with also with Evgeny Tatyakov in Novosibirsk. Evgeny Tatyakov provides us with the compound substituted by metal-nitroxide. And when we do this this methyl group, we have no more the valence tautomerism, but now we have some magnetic order. And the problem was that with this particle, we were able to have a single crystal big enough to determine the space structure. And in the meantime, Utah is moving. It's the same radical with imidazole. So here you have perchlorate PF4, but with that, Utah is using, we're able to make a compound that we have also like the problem was that we don't have a single crystal big enough to know the precise structure. And this was a very important thing. And in the last 2 years, I worked a lot with people in this is the problem in this subject. Because I showed you before that there is two kind of molecular magnets. This becomes very popular now. Most of the people work on single molecule magnet, and very few still work on this system. And I think the main reason is not because they are less interesting. The most problem is because it's very difficult to get single crystal from this system, and because we don't get single crystal, you cannot prove the structure. While with single molecule magnet, there are molecules, it's more easy to get single crystal, so it becomes more popular. So if we want to develop this system, we have to find a tool able to give us the crystal structure. And it's why in the last 2 years, I work a lot with my colleague in Honor to try to use electron diffraction to solve the crystal structure. Because electron diffraction, you can study nanocrystals. And I don't know here, but in France, now there is many places where you have them. But I say that it will be very interesting if we can use electron diffraction to solve the crystal. So electron crystallography is known for many years. The first experiment of electron crystallography was back to the 1930s, but for the coalition compound, it's more difficult because coalition compounds are very sensitive to the electron beam. So the problem is how you can solve the crystal structure without destroying your samples. And so we have tried many things during this years. Finally, at the end, we collaborate with people doing protein crystallography. It is also why it is very important this institute, in this institute, to collaborate between different fields, and it is very important to collaborate between different fields because sometimes we have different ideas. So we start with physicists, and it was very difficult. Then we collaborate also with biologists, and the biologists know very well about using electron crystallography for protein, and this gives us the possibility to solve the substrate. So, thanks to the electron crystallography, finally, we can have the crystal structure of these compounds. So one which was made by Utah with reflect, and the second one which was made by Constance Lecourt when she was internship with Prospective. And thanks to the electron diffraction, we solved the structure. So we have already managed surrounding by radicals. The crystal structure are here. So with imidazole and ferrimagnet and with that, we have this structure. You have to see that this structure is like a corrugated shape. Why we have shape? We think it is because here we use the prefab, so the prefab has the SO3 group and the CF3 group. So there is different bond with the layers that makes this shape. And with perchlorate, but we have almost layered system. When we look to the magnetism is normal magnetism, it's a ferrimagnetic layer that increase, and you have still here the purified layer. If we look to the magnetization, still we don't have a complete saturation, we won't reach 7, but smaller. And here you can see that we have a hysteresis loop, but the hysteresis loop flows at the value which is not the saturated expected value. So this is reminiscent of the weak ferromagnetics and spin counting. And if we look to the magnetization versus magnetic field, so this is the first magnetization. You can see that the first magnetization shows here some points that so this is the reminiscent of metal-nitroxide. And then the valence group that did not superpose with the first magnetic field, which is due to the fact that we have metamagnetism. Metamagnetism is due in the field induced. It's induced by the magnetic. Sorry. Here the SCX-62. So we have it here, and also in the which are not dependent of the frequency, so which I agree is the ferromagnetic ordering at the fluid temperature around 40 degrees. So here we have to consider what makes the difference between valence tautomerism behavior or magnet behavior. So with this one is feedback, this one is perchlorate, this one is perchlorate. We have magnet behavior, and with this one molecule and perchlorate F6. Therefore, we have valence tautomerism behavior. It's difficult when you study the presenter one, but one of the ideas is that to have valence tautomerism, we need some flexibility, because when you have valence tautomerism, you have relocation of electrons from the manganese to the radical, and this induces some change in the conformation, and we need flexibility. If the molecule are too tight, they cannot change. So I think that one of the reasons is that in this compound, the capacity of the structure is less. It is also maybe why it was possible to go crystal with this compound, because they are more soluble. That with this compound, the capacity is stronger. The molecule cannot move, so you cannot have valence tautomerism, and we have this magnet here. So what is the next step? Important information here is that finally it takes a long time to get all this content. Why? Because most of the time we spend to go single crystal. We spend a lot of time to go single crystal only to have the crystal structure. And yes, I finish. With the advent of electron diffraction. Now we can think to new step. And the new step is to have a three-dimensional network. So we have done this. Now we want to go here. To go here, we have to be able to have compounds in which we have only one conformation, delta, or lambda. And for this, we think that we have to use chiral anions. And we have, but now it is more easy to try this route because we have the electron crystallography, and this electron crystallography we can prove the compound, the structure of the compound. Because it's impossible by elemental analysis, because these compounds have the same composition. It's like diamonds and graphite. It's impossible to distinguish them by elemental analysis. There are only tools that can distinguish them in the structure. So we have a project now, like design in this today. While we say something for the students that indeed, when you have million taxes, you have always delta or lambda. If you have delta lambda, which are successive at the net, you have this two-dimensional network. And if you succeed to have delta or lambda, you will have this three-dimensional network. It's not, no, it is not for a long time. The first one who make some dissertation about this was Wells, and he's so it's very interesting because it's difficult. His dissertation was about nets, how we can have nets, and something that is maybe more close to what you hear is or not is finally it is a problem of net. How we can make different nets. Some net will make a two-dimensional network, other will make a three-dimensional network. Now we want to make this one. And also, it's not unknown. I am pleased to show it was a publication of Okawa in the end of. I remember it was still in postdoc, and he tried to publish this publication. We are really troubled because that, in fact, it was right. And so it was in the 90s. And since finally, we have not progressed a lot. We know that if we have alternance, we will have two-dimensional, and if we can be able to have non-alternate, we will have the three-dimensional network. But the problem for this is to have the good tool. We need a tool. The tool is the crystallographic tool. And now we have this electron. So I expect I show you that with nitronyl and combination of nitronyl, we can have some different type of liquids, molecular basement, molecular spin transition, and balance properties. I will need to associate my foundation the people who contribute to this work. It's never work in solitaire. It's we have always many contributions. Many students, students work on the system. The last one is Sabrina Granda, who will come here next summer. Constance Lyon, who was here some time ago. And I want also to thank collaboration. So the group of Holger Klein in the email and honor for the electron diffraction. No need to say in the Institute for Structure of Biology. Of course, the group of Inoue, and it was a major contribution. Ksenia Marionina, who was here when we started study. Evgeny Tretiakov, we have some discussion with him. Also, I collaborate a lot with Christian Miller in Montreal, in Italy now. Hauser from Geneva. Some people for the WPI. and some different institutions. Thank you very much for your attention.